Thank thank you very much for this invitation. It's always a pleasure to give a talk in the TSMS seminar, and today we talk about a deformation of quasi-Hamiltonian spaces. So let me give you an overview of this talk. So we start with the motivation of this project, and then we discuss the background of our deformation theory, such as symplectic manifolds, Hamiltonian spaces, and quasi-Hamiltonian manifolds, and then we dig deeper in the technical issues of this deformation, such as deformation spaces, the main definitions, and the examples of deformations of quasi-Hamiltonian manifolds to their Hamiltonian counterparts. And then, if we have enough time, we'll discuss some future directions to this project. So let's begin with the motivations. The motivation comes from the classic mechanical from physics. In general, when we want to study the phase space of the mechanical systems, in general, it's modeled on the cotangent bundle of the set of all possible configurations of the systems, together with some two form sigma. It's a symplectic form. So later on, we'll explain what do we mean by symplectic form. And if we want to simplify the study of such a system, we would like to find some group of symmetries. And this group of symmetries will act on the cotangent bundle of the set of all possible configurations. And also we have some map mu from the cotangent bundles with values in the dual of the Lie algebra of the Lie groups. And this map encodes the the conserved quantities of the system. And with these three ingredients, we have what we call a classical Hamiltonian manifolds. So we have symplectic manifolds with some group G that acts on these manifolds and some map with values on the dual of the Lie algebra. Then the quasi-Hamiltonian geometry, what we call the quasi-Hamiltonian version of an Hamiltonian system, is a manifold N. In the general case, is a smooth manifold with some two-form omega, and we have some group of symmetry G that acts on N, together with some moment map with values in the group G itself. And with these three ingredients, we form what we call a quasi-Hamiltonian manifolds, the multiplicative analog of an Hamiltonian one. And a natural question arises, can we deform smoothly quasi-Hamiltonian manifolds M to, to an Hamiltonian manifold N? In other terms, if given a quasi-Hamiltonian manifold M and an Hamiltonian manifold N, can we can we deform in a smooth way the manifold M to the manifold N? Now, the questions we have positive answers to this question in three cases. When we take the double of a Lie group, which is a G times G quasi-Hamiltonian manifolds, it deforms smoothly to the cotangent bundle of the Lie group. And when we take the conjugacy class uh, in the Lie group itself, it deforms to the coadjoint orbits of some element X in the Lie algebra of the Lie group. And finally, if we consider the moduli space of uh, G flat connections on some surface with boundary, then it deforms also to some interesting Hamiltonian manifolds. Then in this talk, we try to see this, to investigate these three examples. Okay, then let's start with the first uh, essential ingredients in our theory, symplectic manifolds. So what do we mean by a symplectic manifold? A symplectic manifold is a couple M omega, where M is a smooth manifold and omega is a closed non-degenerate two form. And the basic example of symplectic manifolds are R2n. So if we define the local coordinates x1, xn, y1, yn, then omega is the sum from 1 to n d dxy wedge gyy. So the description of the symplectic form is quite simple in the case of Euclidean spaces of even dimension. And the second example is a standard one. Even if M, our smooth manifold, is not symplectic, the cotangent bundle it does. And in order to define the symplectic form, we define in the first time this tautological form, lambda, using this canonical projection from the cotangent bundle to M, and then we take minus the differential of lambda. And omega, so you can trust me, omega is a symplectic to form of the cotangent bundle. So in the example of S1, the circle, the cotangent bundle of the circle is identified as S1 times R. And if we parameterize the cotangent bundle of the circle with theta and xi, then the expression of the symplectic form is quite simple, is the differential of theta which the differential of xi. Okay? Then, now let's move on to the notion of Hamiltonian spaces. Oh, imagine that we have a compact Lie group G that acts freely on symplectic manifold and sigma. Then, what do we mean by an Hamiltonian G spaces? An Hamiltonian G space is a tuple n, sigma, nu, and G, where sigma is G invariant by the action of the Lie group, and we have some momentum map from N with values in the dual of the Lie algebra, such that the following conditions are satisfied. So if we take any element x in the Lie algebra, and we consider Vx the vector fields on N generated by the action of x on M, then, and if we consider this map nu x, which is a map from N to R, it's a real function, it's a smooth function on N. So the differential, so if we take sigma, if we take the interior product of sigma with this vector field, the first conditions tell us that this interior product is exact. In other terms, the interior product of sigma with Vx is the differential of this smooth function. And the second conditions is that this moment map is G equivariant. Now, if we take an element G that acts on some P in N, then the image of G times P by the momentum map is exactly the coadjoint action of G on nu of P. Okay? Then, first example, the classical one, cotangent bundles of Lie group. Now, the cotangent bundle of a Lie group is a G times G Hamiltonian manifolds. And before this, since G is compact, we can define some scalar product on the Lie algebra of the Lie group, and this scalar product is invariant under the adjoint action of G. Okay, and using this scalar product, we can identify the cotangent bundle of the Lie group with G times the dual of the Lie algebra, which is also identified as G times the Lie algebra itself. And under this identification, we can define the G times G Hamiltonian action on the cotangent bundle. So as you see here, we have the left action and the right action on the first component of the cotangent bundle, and we have this joint action of H on the Lie algebra part. And the symplectic form of the cotangent model of the Lie group is given by this expression. It's quite simple using this inner product. Okay. And finally, the momentum map is quite easy to describe. So to each element AX of the cotangent bundle, we associate the adjoint action of A on X and then minus X. And each one, the adjoint action of A on X represent the moment map for the left action of G times G on the cotangent bundle, and minus X represents the right action or the moment map that corresponds to the right action of G times G on the cotangent bundle. Okay? And then, lovely example, when we take G equal to S1, the circle, we get sigma. Sigma is quite easy to describe because it's simply one y1 z2 minus y2 z1, and since S1 is abelian, the Lie brackets of y1 and y2 is equal to 0. Okay, and then and also the moment map, it's not complicated to describe because it's only x and minus x. Because as we said before, the circle is abelian as a Lie group. Then the second example, co-adjoint orbits. Now, again, using the scalar product that we introduced before, we can identify the Lie algebra with its dual. And if we take an element in the Lie algebra, the co sorry, sorry, yeah, sorry. And if we take any element in the Lie algebra of the Lie group, the co-adjoint orbit is described as follow. It's only G of x, and G is only the adjoint action of the group G on the Lie algebra for any element G in the Lie group itself. And this co-adjoint orbit is G Hamiltonian manifolds. So how can we describe this Hamiltonian structure? So the action is by conjugation, and the inclusion map is the momentum map for this action. And the symplectic to form is given by the following formula when we take V1, V2 to be elements in the Lie algebra, and if we consider uh, the vector fields xv1, xv2 generated by the action of v1 and v2, then their image under the symplectic form is the scalar product of y with the Lie bracket of xv1 and xv2. Okay, then enough talk with the Hamiltonian spaces. Let's move on to the second ingredients, the quasi-Hamiltonian spaces. The second ingredients which are that they are essential in our deformation theory. So, as we said before in the introduction, the quasi-Hamiltonian spaces are the multiplicative analogues of Hamiltonian manifolds. But in which sense? So imagine that we have a compactly group that acts on this on some manifold M, with together with some two form omega. Then a G quasi-Hamiltonian manifold is a triple M omega mu, when mu is a smooth map called the momentum map with values in the Lie group G itself. And then we have that omega is a G invariant two form, such that omega verify the three conditions. We have that the first one tell us that the differential of omega is only the pullback of some special free form kappa by the momentum map mu, and then we have a description of the interior product of omega with VXC in terms of the momentum map and theta L and theta R. For information, theta L and theta R are the left invariant and right invariant molar Cartan form defined on the Lie algebra. And for any element P in the manifold itself, we have this description of the kernel of omega P in terms of the VXC, where VXC is the vector field on M generated by the action of Xi on M itself. And as you see, we, we have some difference between quasi-Hamiltonian spaces and Hamiltonian spaces. Why? Because in the case of Hamiltonian spaces, we already said that omega, the two form, is closed. But in this case, the omega is not necessarily closed. It's only the pullback of this three form kappa by the momentum map. And also, in the Hamiltonian case, the two form omega is non-degenerate, which is not the case in the quasi-Hamiltonian manifolds. The two form omega is not necessarily not degenerate. And the third remark is that the momentum map in the Hamiltonian case has values in the dual of the Lie algebra, but in the quasi-Hamiltonian manifolds, the momentum map has values in the Lie group itself. Yeah, it's already mentioned in this paragraph, a key difference. And omega in the moment maps takes values in G, not in the dual of the Lie algebra, and omega, the two form that we defined on the manifold M, is not necessarily non-degenerate. Okay, so this is the formal definition of quasi-Hamiltonian spaces. Then let's move on to see some maybe basic examples of quasi-Hamiltonian manifolds, and then we start with the double. The double of G, which is equal to G times G, is G times G quasi-Hamiltonian manifolds. And how we describe this structure? First, we define the action of G times G on the double. And as you see, we have this left action and this right action on the first component of the double. And then we have this the adjoint action of H on B. Sorry, I wrote X, but actually it's not X, it's B. Okay, so we have the add hash applied to B, not to X. Sorry for this misunderstanding. And the moment map this time has value in the in G times G, and this moment map is given by the following expression: to a couple AB, we associate AB n minus 1 and B minus 1. And this two form omega is given by the following expression. Uh, it's not a beautiful expression to give, but this is how it's defined in the case of the double. Okay, lovely example. Always with the circle. If G is the circle, S1, then the momentum map, then the quasi-Hamiltonian structure is easy to describe because the momentum map is given by B and B minus 1, and the quasi-symplectic to form is given by the following. So if you parameterize S1 by theta, then we take uh, the pullback of the differential of theta by A, which the pullback of theta by d theta by B, where A and B are the first and second projection of G times G on G. So it's quite easy to describe also. And now, second example, fusion products of quasi-Hamiltonian manifolds. Now, imagine that we have, before we talk about fusion products of two quasi-Hamiltonian manifolds, let's discuss a little bit what we call an internal fusion of quasi-Hamiltonian manifolds. So imagine that we have some G times H quasi-Hamiltonian spaces with three moment maps, mu1, mu2, and mu3. Then the internal fusion of M is the G times H quasi-Hamiltonian manifolds. So the idea is the following one. We start from G times H quasi-Hamiltonian manifolds, and we want to construct some G times H quasi-Hamiltonian manifolds. So what we do is we take these two copies of G and we glue them. We apply some fusion to these copies, and then we get a new quasi-Hamiltonian structure on the same manifold M, but this time it's only G times H quasi-Hamiltonian manifolds. And it's described by the following momentum map. So when we when we apply a fusion to these two copies of G, we get mu1 times mu2 as a moment map with values in G, and then we don't change the momentum map mu3, which has values in the Lie group H itself. And then how to define the fusion product using this internal operation. So imagine that we have uh, two manifolds M1 and M2, and each one is M1 is G times H1 quasi-Hamiltonian manifolds, and M2 is sorry, and M2 is G times H2 quasi-Hamiltonian manifolds. Then the fusion product of M1 and M2 is simply uh, M1 times M2, on which we apply the internal fusion to the G copies. In other terms, we take M1 times M2. M1 times M2 is a G times H1 times G times H2 times H2 quasi-Hamiltonian manifold. And when we apply the fusion to these two copies of G, we get a G times H1 times H2 quasi-Hamiltonian manifolds. And with this description of the moments map. So for the G, for the G copy, we have mu1 times mu3 as a moment map with values in G, and then we don't touch at the rest of the moment map components. So mu3 is the moment map with values in H1, and mu4 is the moment map with values in H2. Okay. Then let's discuss maybe one of the important construction of our Hamiltonian deformation, known as deformation space of a Lie group. So we have a Lie group, and then we define these spaces, what we called a deformation spaces of G and 1. Then the philosophy is simple. Then imagine that we have these two pieces. We have G times R star, and then we have the Lie algebra times 0. And each one is a smooth manifold, but we want to glue them to get some connected manifold into, sorry, we want to glue these two pieces into a connected manifolds. And this connected manifold is what we call a deformation space, DG1. And this spaces is equipped with the unique smooth structure such that this projection from this deformation space DG1 to R is a smooth submersion. And then we have a key lemma, some sort of how to say, parametrization of the central fiber. In this case, the central fiber is the Lie algebra, and with this map, phi, we define is this map phi is smooth, and it defines some local coordinates of a neighborhood of the central fiber, which is isomorphic to G times 0, the Lie algebra of the Lie group. And this lemma is important because we will use this map to define our Hamiltonian deformation. So we keep that in mind for the furthest constructions of examples of deformation theories. And then the funniest part of our paper is the Hamiltonian deformation. Then imagine that we have a quasi-Hamiltonian space and an Hamiltonian one. How can we define an Hamiltonian deformation from this quasi-Hamiltonian manifold to this Hamiltonian manifold? Then, an Hamiltonian deformation is only a smooth manifold D together with some G action on D, submersion from this manifold to the set of real numbers, such that the compact interval 0, 1 is included in the image of P, and we have some moment map mu hat from D with values in these deformation spaces that we defined before. Recall that G is only DG1. Okay, sorry. And this moment map mu hat is equivalent with respect to the conjugation action. Sorry, with respect to the conjugation action on G itself, such that, and also we define some smooth form omega hat on this manifold D, such that if we consider the restriction of this moment map and the smooth to form on each fiber, then for T different from 0, the fiber itself is isomorphic to M as a G quasi-Hamiltonian spaces. At this time, it's not the original M, but we take omega, the quasi-symplectic to form, and we divide it by 1 over T. So each fiber of our manifold D is isomorphic to M with this with this new quasi-symplectic to form as a G quasi-Hamiltonian spaces. And when T is equal to 0, the central fiber D0 is the G Hamiltonian manifolds, and D1 is isomorphic to M, and D0 is isomorphic to N as quasi-Hamiltonian and Hamiltonian spaces. Okay, then first principal result of our paper. How can we deform the double, which is equal to G times G to the cotangent bundle of a Lie group? And this space, D, which is equal to G times dg1, we recall that this space is only the is simply the deformation space of the Lie group. We defined this in the previous slides. So G is this one. It's only the deformation spaces of this Lie group. And then if we take this manifold G times dg1, then this one has the structure of an Hamiltonian deformation from the double to the cotangent bundle. Uh, to define the most challenging part in this construction in this theory is to define the two form omega hat in the case of the double. And the idea is the following: if we are away from the central fiber, so we can define omega hat to be omega times t, omega over t. Okay, but when t goes to 0, this quantity goes to infinity, and this is a problem because we want to define a smooth to form omega hat on the whole deformation space. So the idea is to use this map phi, because this map phi is how to say it, parametrization of a neighborhood, of an open neighborhood of this central fiber over 0. And then using this map phi, we define a new form on this neighborhood. And this new form, for example, we call this new form eta. And eta when t, and what is the property of this new to form defined on this neighborhood? When t goes to 0, eta converges to the symplectic forms of the cotangent bundle. So at the end of the day, we have two forms. We have, sorry, so we have two forms. One form is defined away the central fiber when t is different from 0, and we have a second two form which is defined on the neighborhood of the central fiber. And both of them are smooth, but the goal is to define a smooth two form on the half deformation spaces D. The idea is simply to glue these two forms using a partition of unity. And when we choose a suitable partition of unity, we can glue both of them to get a smooth two form omega hat on these deformation spaces. So it was maybe the most challenging part when we wanted to define when we wanted sorry to deform the double of G to the cotangent model of the Lie group. And then let's move on to the second principal results of our paper. So if we take some element in the Lie algebra of the Lie group, such that the definition of the exponential is invertible for any t in 0, 1, and we consider the open interval on which the exponential is invertible. And if we take the image of x by the exponential map, and if we consider the conjugacy class of the exponential, which is a subset of the Lie group itself, and then we take the coadjoint orbit of x, which is also a subset of the Lie algebra of the Lie group, we recall that the conjugacy class of the exponential is G quasi-Hamiltonian manifolds, and the coadjoint orbit is a G Hamiltonian manifolds. And then, if we define this set C in this way, so we take the union of the all conjugacy classes of the exponential of Tx, and then if we consider the coadjoint orbit of x times 0, we take the disjoint union of them. Then the set C has the structure of an Hamiltonian deformation from the conjugacy class of the exponential of x to the coadjoint orbit of x. And finally, uh, we have some other results about other results that discuss this compatibility between fusion products and Hamiltonian deformations. In which sense? So imagine that we have an Hamiltonian deformation from a G times G times H quasi-Hamiltonian space to some G times G times H Hamiltonian manifolds. Okay, then we can define a natural deformation theory from the internal fusion of M, which is G times H quasi-Hamiltonian manifolds, to the internal fusion of N, which is a G times H Hamiltonian space. And then the corollary of this theorem is that if we have two quasi-Hamiltonian spaces that admit Hamiltonian deformations to some Hamiltonian manifolds, then the fusion product of M1 and M2 deforms also in a smooth way to the fusion products of N1 and N2 in the Hamiltonian category. Okay, and we will use this theorem and this corollary to describe the deformation of the moduli spaces of the moduli space, sorry, of flat connections on surfaces with boundary. Then the third one, the third principal result of our paper concerns this moduli spaces of flat connections. So imagine that we have some compact connected oriented surface of genus G with R plus 1 boundary components, okay? And then we consider this moduli space of flat connections on the trivial G principal bundle over this surface. A nice theorem of Meirinken and Alexeev tell us that this moduli spaces has a nice R plus 1 quasi-Hamiltonian structure. And this quasi-Hamiltonian structure is beautiful, it has beautiful descriptions in terms of the internal fusions of copies of the double of G and the internal fusion of the double of G itself. Then the R time we have the first part is fusion products of R copies of the double of G, and we have fusion products of copies of the internal fusions of the double of G itself. And then we defined in this paper, we defined an additive version of the moduli spaces. So to each copy of the double, we associate the cotangent bundle, and to each copy of the internal fusion of the double, we associate this. We can call all. We associate also some uh, a version of an internal fusion of the cotangent bundle itself. And in this time, and we have also some we have let's say a geometric interpretation of this additive version, because to this surface we can associate what we call the quiver. So it's a connected graph with some properties, and on this quiver we can define some differential equations, what we call the Lax-Kirchhoff equations. And this space of differential equations have uh, a symplectic, natural symplectic form, okay? And we define some gauge group that acts on this moduli on this space of these differential equations, of these Lax-Kirchhoff equations. And then, if we consider the moduli space of solutions of Lax-Kirchhoff equations, then this moduli space is a smooth symplectic manifold, which is isomorphic to this product. Okay. So it's some geometric interpretation of this additive version of the moduli space of G flat connections over sigma. Okay, and then the expected result is that we have an Hamiltonian deformation of the moduli space of flat connections on sigma to this additive version that we defined before. And this corollary is just an application of our theorem 3.1 and the corollary 3.2. And the idea is to deform each component uh, to to deform the double of G to the cotangent bundle, and then we deform also the internal fusion uh, of the double to the internal fusion of the cotangent bundle. Okay. And then open questions and future work. How can we extend the deformation theory to quasi-Poisson manifold settings and stratified quasi-Hamiltonian manifolds? Actually, it's a paper in preparation. Uh, if we take Hamiltonian quasi-Poisson manifolds, how can we deform them to get Hamiltonian Poisson manifolds? And this is the first settings, and the second one is about stratified quasi-Hamiltonian manifolds. So if we have some singular quasi-Hamiltonian manifolds, and we have also stratified Hamiltonian manifolds, how can we define a similar theory to deform a singular quasi-Hamiltonian manifold to some singular Hamiltonian space? Okay, and I already find some examples of quasi-Hamiltonian Poissons that deform to some Poisson manifolds. For example, if we take a Lie group G is also it's an Hamiltonian quasi-Poisson manifolds, and we can deform this structure to get the linear Poisson structure on the dual of the dual of the Lie algebra of the Lie group itself. And also, this kind of this theory of quasi-Poisson manifolds extend in some sense uh, our deformation theory of quasi-Hamiltonian manifold, because um, non-degenerate Hamiltonian quasi-Poisson manifolds are equivalent to quasi-Hamiltonian manifolds. So it's some generalization of our work in the case of smooth quasi-Hamiltonian manifolds. And the second question is, can this deformation be quantized? What happens to quantum Hamiltonian structures? And the third one is, if we have non-compact groups, or if we have groups without an invariant metric, can we also define similar deformation theory from quasi-Hamiltonian spaces to Hamiltonian manifolds? And yes, thanks for your and thank you very much for your listening.